And this is data communications assignment 3, group 4. This assignment we will have 4 tasks, and me and Hung will walk you through all of that task. So firstly, for task 1, the requirement is to design and configure routers, verify the network, assign class C private IP. So for class C private IP, we are using a 65,536 IP address in totals from 168.0.0 to 168.255.255. The task has have 4 subnet with 4 PC and 1 subnet with 8 PCs. Here, I'm gonna showing you here. We have a subnet A to C is used subnet mask 29, which have 8 hosts and usable 6 hosts. Subnet D, I use a subnet mask 28, which 16 hosts and 14 usable hosts. I will demonstrate the ping case. So for right here, you can see the it's sent successfully down here.
Now, moving on to task 2, the task are to split the subnet into 2 VLANs. For this, I choose to split the subnet B into VLAN 10 and VLAN 20, effectively creating 2 isolated network segments inside the same physical switch. This segment helps control traffic and improve network organization. As you can see, I have assigned BC4 and 5 to VLAN 10 and BC6 and 7 to VLAN 20, which confirm the VLAN membership of each port. Although the task run will require testing intra-VLAN connectivity, but I confirm my network to inter-VLAN routing as well. This let me demonstrate the difference between intra-VLAN and inter-VLAN communication. And first, I will test intra-VLAN connectivity by sending a ping from BC4 to BC5 where both in VLAN 10. The ping was successful. As you can see, this communication happened at the layer 2 in a switch, where the switch forward a frame directly between devices in the same VLAN without involve a router. And next, I will show the inter-VLAN connectivity, which I ping from BC4 in the VLAN 10 to BC6 in the VLAN 20. This is also success because I configured the router on stick setup to route traffic between VLANs. In this case, the traffic leaves the switch and go through the router, which route the packet between 2 separate VLAN subnets. And to further demonstrate the role of the router in the inter-VLANs, I will disable the router interface. Shut down. As you can see that the ping was failed because without router for routing, device in a different VLAN cannot communicate. The switch can route between VLANs, it only switch within a VLANs. Lastly, intra-VLAN traffic stays within the switch at layer 2, allowing devices in the same VLAN and subnet to communicate directly. For inter-VLAN traffic, it requires a router at layer 3 to route packets between the VLANs, since VLAN isolates the broadcast domain. When I disabling the router, it confirms that the routing is necessary for inter-VLAN communication, while intra-VLAN communication works independently of the routers.
Layer 3 evaluations of subnet B clear the ARP table on the devices and ping a host to other subnet from subnet B to subnet A. Analyze and demonstrate how layer 2 and layer 3 addresses provide a detailed explanations of those address change. Now I will demonstrate you. So here we have the thing, and now we'll send for PCPT 8 to PCP 8. So now if we click here, we can see the IP header of here, and the other one is FF89, and the PC8 is trying to send the data to another subnet. And in the IP networking, when a host wants to communications outside of its subnet, it must forward a packet default gateway. Layer 2 Ethernet communications always use a MAC address when routing other networks via IP. Switch in subnet C send the request all connect device including router B. Once receiving an ARP request, router B respond with a MAC address, allowing PCA to update the ARP here, and the router B sends the MAC address back to PC8, which update the MAC address from FFF TOTHE to here. The layer 3, the send of the ICMP echo request. Now the PCA. Oh. Okay. Now the PCA is sending the default gateway. It's constructed to send ICMP echo request. The packet handlings are as follows. Here, the package is send switch which forward to router B. Here, forward to router B. Here, port A serials, and the router B is received the ICMP strip layer 3 headers to check the IP header. It's C the belong to IP belong to subnet A. Right here, A, and according to routing tables, the forward is packaged to router A. And now the package is to the destinations. The PC1P here. Here, the port has reached its destinations. The router A received the ICMP and request from router B. It's read the destination IP address, and in the IP headers, the consult routing tables confirming that the destination is in the subnet A, which directly connected. Since the router A already has PCO MAC, the ARP table does not need to send an ARP request. Router A can construct a new Ethernet frame, and the packets forward to switch A, which already has PCO MAC in it, MAC address tables, and deliver direct to PCO. And now we're moving on to task 4.
Now moving on task 4, which involves setting up a web server in one subnet and explaining how the decoding and encoding of the HTTP requests flow to the OSI 7-layer models. As you can see that I place a web server in the subnet D and assign the IP and enable HTTP service, which ensure that all IPs across the network can reach it. Here's an example. Success. And now I will show how HTTP request is encapsulated, encoding, encapsulated. Okay, again. And now I will show how HTTP request is encapsulated in the OSI model when the user. And now I will show how HTTP request is encapsulated in the OSI model when a user sends a web request. The encapsulation process will be encoded from the top layer and moving down to a bottom layers. In the application layer, where the browser creates the HTTP request, usually we can see a GET request for the index page, but since we didn't configure a home page, so it just connects to the server we are asking for in any page. And moving down to layer 6 is not directly visible in the packet tracer, but it responds for encrypting the request if we use the HTTPS through the SSL or TLS. And in layer 5, section management is handled by TCP. It tracks and manages the communication section between the client and the server, which making sure communication is set and maintained. And moving to a transport layer, the system adds the TCP header This includes source and destination port number. Usually port is 80 for HTTP, or if we use HTTP, it's the 443. And this is how the system knows which application to talk to on the destination device. And then the network layer wrap the TCP headers inside in the IP header, which contain a source and destination IP address telling router where to send the package. And at the data link layer, the IP package is wrapped inside internal frame, which assign a MAC address, which allow local delivery between devices on the same network. And finally, the frame will convert into a bit and send across the cable to a next device. So next, we're gonna look at how this encapsulated data flow to the network. So the frame first arrives at switch A, which check the destination MAC and forward it to a router based on the MAC table. The router remove the LA2, which is the internal head. Since it's only for a local section, so it's estimate the IP header, which is layer 3. Then determine that the next hop is subnet C, so it's gonna re-encapsulate the package with no MAC address and send to a switch D, which forward to a web server based on the update the MAC address. And at the server side, the process happens in reverse, starting from layer 1 moving up to the and layer 1 and moving up. Where first at layer 1, the physical layer, the server receives the raw data over the cable. And next at layer 2, the data link layers, the server will remove the Ethernet header to reveal IP packet inside. And like moving to layer 3, the network layers, the server will check the destination IP address to make sure it matches on. And then the server will remove the TCP header to see the destination port is 80, which is the standard port for HTTP, which confirming it should handle this request. And finally, at the level 5 to the 7, the section, the presentation, the application layer, the server will re-establish the section and process the HTTP request. And after a processing, the server will prepare the HTTP response and send it back to your client by encapsulating it through the same 7 layer, but just in the reverse order of this. And that's how request is encoded and decoded throughout the OSM model. Finally, thanks anyone for watching.